thank you so much for being here. Thank you so much for listening. I know I'm between you and drinks at the reception, so I'll try and make this entertaining. I wanted to start out with an important question for you all. Just why am I here? And I wanted to tell you that the reason that I'm here and the reason that this talk is about it, or the reason that all of the things that we did to lead up to this moment happened is because I'm incredibly excited about empowering people to build systems that they might not otherwise have been able to build. I think there was a lot of great stuff that Ben talked about how some of these tools allow you to debug systems that you might not otherwise be able to debug. Today I want to talk about how we can enable people to build systems that they might not otherwise be able to build. And 2 years ago at the initial KubeCon, I said that I wanted to make distributed systems a CS 101 exercise. I think that's still the mission, and I think that sadly, maybe we haven't made as much progress on that as we might have hoped or as I might have hoped. So I want to take a step back today to talk about some new ideas that have been bubbling around in my head for a while about how we can work towards that mission. I wanted to start motivating this by taking a look at the process of development in a cloud-native world right now, right? There is your code, there is compiler that turns it into a binary that you then write a Docker file for, and the Docker tool that turns it into a Docker image that you push to a container registry. Then there's Kubernetes, which is a cluster, and a kube control, and a YAML config. There's a lot of stuff, right? And a lot of tools, and a lot of different languages, right? You've got at least 3 files, you've got at least 3 languages, and you've got at least 3 tools. And in many cases, you have many more. Right? This is even before you throw in a CI/CD system or any kind of higher level development system. It is no wonder that it is too hard to build distributed systems today. The set of tools alone, and by the way, there are 3 of these, and each one of them has like 5 different choices that you could make, right? So the set of decisions you have to make before you even start thinking about your application is extraordinarily daunting. And it's worse than that. It's not even just about sort of cognitive overload. It's actually about the fact that we have information scattered across all of these different systems. Consider like the port that your server listens on. Well, it's in your code, clearly, because you have to listen on that port in your code. It's probably in your Docker file, so that you say that I'm exposing this port in the image. It's definitely in your Kubernetes config, so that it tells the service what port to talk to. And there's no linkage that draws those pieces together. So heaven forbid that you go and do something like change port 80 to port 88. And remember to do it in your code, and remember to do it in your Docker file, and forget to do it in your Kubernetes config, right? You're going to push that config out, service isn't going to work, hopefully you catch it early, but the very fact that you have to cut and paste that value across all of these different systems points to the fact that the job is too complex. We have not done enough work to view the entire process of building and deploying and managing an application as a single problem. I'm going to highlight that with an arrow. Oops. All right, so this leads to one of the first principles, because I've been thinking a lot about why is this hard? Why is this, what can we do to make this easier, and what can we do to make this better? And it led to the first principle that I had that wanted to guide the system that we're going to build. And that's, I really think we have to have everything in one place. We have to have one way of specifying the ports that we listen on, one way of specifying the topology of our application, one way of talking about where we want images to reside. We have all of these different pieces that are scattered across all of these different files. We really need to have a single source of truth, a single place where we go to understand our application. You might be deploying a replicated system with sharding and things like that. It's not like the code could be used in a different environment, and yet you've represented the deployment of that code in a YAML file while the code itself is in some programming language. It's just not a recipe for success. But at the same time, we've seen other approaches to this across the history of cloud, platform as a service and other things that try and kind of give you this everything in one place opportunity. But we've also seen that those are ultimately restrictive in ways that lead people back towards more raw infrastructure. And so what that leads to is the second principle, which is that we need to build libraries, not platforms. I need to be able to opt into the pieces that are useful to me, leave behind the pieces that are not, and have escape hatches in the right places so that when I hit the walls of the environment, I have places to go. So if principle 1 is that we need everything in one place, principle 2 is every once in a while I need to go someplace else. And then the third part of this is, as we've seen this incredible community develop, as I've seen all of these people come together with all of these great ideas to build things that we never even thought of, we need to encourage sharing and reuse. Across the history of compute, the way that we make things easier is by building a single implementation that everybody shares, right? It used to be long ago that people built their own GUIs. People built their own button implementations. People, splatted pixels directly onto the screen. No one does this anymore. We all use windowing toolkits because that's an expected library. It's a shared library. There are people who focus on that, but most of us simply consume that. We need to think more as we build distributed systems. How do we build reusable components that actually allow us to put our systems together? So how do we do this? How do we go and build this system that allows us to make distributed systems easier, follows these principles that I think are all important? Well, I think it's all leading, and I see different places around in the container space and elsewhere. I think it's all leading to what I've been calling lately language idiomatic cloud. I think that there is no reason that the one place where you need to build everything shouldn't be a programming language, right? We know programming languages well. Anybody who's in the config space and the YAML space understands that configuration ultimately becomes a Turing-complete programming language. It's just a very poorly designed one, right? So why not start with a language that has been designed with these thoughts in mind? Why not start with languages where there's already tooling and editors, there's already unit tests? How many people out there unit test their configurations? I'm guaranteeing you the number is a lot lower than the number of people who unit test their code, and yet, shouldn't we be unit testing them both? And that's only possible, it's not only possible, but it's significantly easier if you're already in a programming language that has unit test libraries, that has unit test frameworks. All of these benefits that we get from the programming language should apply to the configuration and deployment of our systems as well. Additionally, they're more approachable, right? There are a large group of people out there who are lucky if they've sort of managed to master a single programming language. Asking someone to learn a programming language and then a Dockerfile language and then a YAML configuration language, as well as all of the tooling that goes with them, is simply reducing the set of people to whom this technology is approachable. We need to expand the set of people who can do this, not put up barriers to entry. I mentioned the better tooling. And then finally, we're already starting to see people want things like inheritance, abstraction in their configuration files. Why are we going to reinvent the wheel that programming languages have been, and people who think deeply about programming languages have been focused on for the last 30, 40, 50 years, right? So I think over the next 5, 6, 7, 10 years, we're going to see the development of language idiomatic cloud, where cloud is a language feature. Just as locks went from being assembly language instructions to being libraries, to being standards like POSIX, to being language keywords like synchronized in Java, we're going to see cloud and cloud native abstractions move from the assembly language of Kubernetes to being language features of future programming languages. I'd like to point out that I actually don't think that this is a new idea. Someone once said, the future is already here, it's just not evenly distributed, right? It's a quote that a lot of people have heard and something that I think about a lot. If we take a look at things like Hadoop, Hadoop said, hey, if you implement this Java class, this set of Java classes, I will give you a distributed system. It's targeted to a very specific use case, MapReduce, but it's a clear example of how you can bring a language idiomatic cloud to a distributed system environment. More recently, there's been work on this thing called PyRen that some people may have looked at, and they basically took the Python map function and they wrote a backend that uses functions as a service to parallelize your map. Suddenly, everybody who can write a Python map function has access to a supercomputer, has access to the cloud without them even knowing about it, right? This democratizes distributed systems in a way that is unlike anything that we have seen up to this point. But these are targeted to very specific use cases, and I think what we need to do now is to actually say, how do we take these example proofs and build the general system? And by the way, this was always the plan. This is something that has been in the back of my head for a long time. In containers, we have an analog for objects. In Kubernetes, we have an analog for the runtime, for the CLR or the JVM. But there was always a standard library that went with that runtime. And so the question becomes, where does that standard library come from? And I'd like to introduce today a standard library for cloud-native computing that I've been calling Metaparticle. And so we'll spend the rest of the time talking about Metaparticle and giving some ideas about how we might expand this into the future. Because I will say that Metaparticle is an experiment. It's highly likely to need serious adaptation. It may even be completely wrong, but I am highly confident that something like this will be the way that we actually bring cloud-native computing to the world, to CS 101, to hobbyist programmers, to my kids in middle school. This is going to be, language idiomatic cloud is going to be the way that we bridge that gap. All right. To give you an example of how this works, I want to take a look at a very simple Java program. This is a very simple web server in Java. It just says, hello, Metaparticle. Let's take a look at how we take this Java application and containerize it. So we're using language level features. We're using Java annotations and a simple wrapper function. In the previous program, when you ran it, you got a web server. When you run this program, you get a container image pushed to a registry. Right? By adding these annotations, I've actually created an executable that knows how to package itself as a container, knows how to push itself up to the registry. And by the way, this isn't just in Java. You can do the same thing in JavaScript. Right? The same idea, I don't have annotations in JavaScript, but we have this pattern of function pointers, options objects. I can pass the same information that I passed in that annotation as an options object to JavaScript. It will package itself as a container, push itself up to a registry. It's very easy to see that not only is information like the port number preserved through the code to the Docker file, ultimately to the Kubernetes YAML, but also I didn't have to teach anybody anything. If they knew JavaScript, they can containerize their application. And I think that the thing that allows us to do this in all of these languages and to be idiomatic within all of these languages is viewing Kubernetes and containers effectively as a compiler target. Right? And so if you look at the details of Metaparticle, this is what it looks like under the hood. There's code bindings for each language. There's an intermediate representation. There's a compiler that knows how to take that intermediate representation and compile it into containers and Kubernetes objects. And so obviously packaging something up as a container is the extent of what you want to do. We actually want to be able to deploy it to the cloud as well. So if we take a look here, I'm adding one additional annotation to my Java program that I had before, and that's that I have a runtime with replicas equals 4. Right? And this is said, actually, not only do I want you to package it as a container and push it up to a registry, but I want you to deploy it to Kubernetes with 4 replicas and a load balancer in front. So let's see a demo of this in operation, hopefully. All right, so there's my code. You can see here the runtime annotation. You can see the package annotation that's there. You can see that simple Java server. I'm going to quit there. Now what's happening in the background is I'm actually running my application, and it's building itself to pick up any changes to the code that I might have had. In just a second, you can see that it's building up a jar. In just a second, you're going to see it's packaging itself as a container. It's pushing itself to the registry. And in just another second, it's going to have deployed itself to Kubernetes. And it's detected the logs. So something else that it does to give you the illusion that it's running on your machine, it's actually attached to the logs that are coming off all of these containers. And now I can see, actually, if I do kube control, hey, I've got some services. I've got that web service that's up and running. If I look, I've actually packaged this thing as a deployment. There's 4 replicas in the deployment. And if I run a container inside my cluster, I can actually go and hit that load balancer. So I can say wget And there's my code running on that code that I had in that Java application running replicated 4 times up in the Kubernetes cluster, just by running that Java executable. It's nice of you. It gets cooler, don't worry, it gets cooler in the 4 minutes that we have left. And you can see there that it's actually hitting multiple replicas. All right, so let's exit out of that. And go back. This is always the part where I'm like, hope that it doesn't go back to the beginning of the text. Yes, all right. Mastering PowerPoint. All right, but if you can replicate things, the obvious next question is, well, what about synchronization? If you can replicate lots of replicas and they run on multiple machines, one of the hard problems that everybody immediately runs into is how do I synchronize things? Well, it turns out that this needs to be part of the standard library as well. So here it is in JavaScript. I can pull in the Metaparticle sync library, I can create a lock, I give it a function callback. When the callback is called, I have the lock, and then I can release the lock if I want to do it, right? Familiar to people who do JavaScript, familiar to the JavaScript idiom. Of course, if you're going to do it in Java, it looks a little different. I'm going to create a lock class, I'm going to be able to lock it, I'm going to say I have the lock, I'm going to unlock it. By the way, in Java, there's actually an abstract lock class that this lock implements. So I can actually pass it. Anywhere that expects a lock, I can pass this class around. But it's a distributed lock. How is this built? Well, again, we want to build it in such a way that it's language independent. So we're going to use a sidecar. We have a user code that is a very thin language wrapper around a sidecar container. The sidecar container is a shared implementation that anybody can use. It uses custom resource definitions in Kubernetes to create this custom resource lock. All the locks go through that. By the way, this also means I can use Java and JavaScript and have the same lock object, right? So I'm assuming that I have these cloud-native primitives, and I'm building language-level bindings to make them more approachable. I'm bridging the gap between a cloud-native abstraction and a language feature. By the way, if I have locks, well, it actually is quite easy to then do election and to do master election. And so here is the JavaScript code to do master election. Pull in the library again, create an election object, give it a name, obviously the shard that I want to do election on. First function is called when you become the master. Second function is called when you lose the master. Now, I think it's clear to understand that this is way more approachable, way more likely something that you can teach to someone than giving them, the etcd manual and telling them to figure out how to do distributed locks, right? And so I think, again, what we're trying to do is bridge the gap between cloud-native ideas and a language-level primitive that people understand. And finally, I think this is all part of the development of patterns for distributed systems. I think to this point, the construction of distributed systems has been artisanal at best. There's a lot of leather and copper and hand weaving that's going on as we build distributed systems. And I think at some level as craftspeople, we like that because it makes us feel important. We need to be in the business of mass production. It's the only way that we will scale to the number of systems that need to be built, and it's the only way, honestly, that we will build reliable systems. So to give you an idea about how this looks, consider sharding. Sharding is the process of having a request that comes into a service, and then all requests for a particular shard go to a particular server. Different requests come in, they go to a different server. So hashing on the username, for example. With Metaparticle, you can again do this, the same annotations. In this case, instead of saying replicas equals 4, I say shards equals 4, and I add something else, which is the shard expression. It's a regular expression that applies to the HTTP path that tells me what chunk of that request I want to use as my shard key. So in this particular case, I'm sharding on the username. Every single request for the same user will get sharded to the end to the same server. And again, because I put it into the language, when I compile and run this application, and sadly I don't have enough time for the demo, but when I compile and run this application, it deploys itself as a sharded system. It deploys a load balancer, it deploys a sharding front end, it deploys the shards themselves as a stateful set, and it links everything up with load balancers and reusable container components that are part of this standard library. Skip through the demo in the interest of time, and I want to say this is really just the beginning. It's an open source project that's available out on GitHub at metaparticle-io or http metaparticle.io. Twitter, anywhere else, come talk to me after the conference. I'm incredibly excited about how together we can build the standard library that truly democratizes distributed systems on top of Kubernetes. Thank you so much.